Okay, so 10-2 vectors. Some of you learned vectors in your physics honors class a little bit. You saw it again in AP physics. Some of you aren't even in physics. You guys did take it in pre-calc last year. Okay, so what is a vector? So I kind of could just categorize this. I thought I would explain to you what a vector looks like when you write it. So there are many ways to write a vector. Some people write, 3 comma 4, or 3 comma negative 4 maybe. They'll write that. Some people actually write it a little differently. They'll write it with 3i hat minus 4j hat, which really just means the same thing. Okay? And in this classroom, we will use the bracket notation. We will not use the I hat, j hat standard unit vector notation. So I'm going to erase that one. You don't need it for my classroom. So 3, negative 4. What does it mean to have a vector 3, negative 4? It literally means this. You're going to be going right 3 and down 4. So this is the vector 3, negative 4. It should be aiming a little bit steeper. Let me steepen that a little bit. 1, 2, 3, 4. So the vector 3, negative 4 looks like this. From tail to head, it's right 3, down 4. Okay? Now the vector 3, negative 4 has its own length, but it's longer than 3 and 4. Right? This is just sort of instructions on how to draw. It means right 3, down 4. It's kind of like run and rise is what it is. It's run and rise. Let's label those real quick. First number is run. The second number is rise. Okay? Which means you really could draw it wherever you want in space. It's kind of like a geometry figure. If I said, everybody draw a triangle, you don't need an XY axis for that. You just draw a triangle on your paper. Some of you draw it upside down. If I say, hey, draw an isosceles triangle, some of you draw this. Right? Some of you draw this. I didn't say which orientation to give, right? So there's no orientation necessarily on a vector in terms of where you draw it. But it's important that you have it right 3, down 4. Because if you change that direction, let's say you do right 4, down 3, it's going to change the angle of tilt. And you don't want that. So this is a different vector. These are not the same. This is the vector 4, negative 3, you see. A little bit different. Over 4, down 3. Okay. What these vectors both have in common is they have the same length. That is true. They're both length 5, but they're different vectors. All right? So those are not the same. Most people draw their vectors in standard representation. That means they'll draw an XY axis. And when they're told to draw the vector 3, negative 4, they will start right at the origin and go right 2, 3, down 2, 3, 4, and draw their arrow. That's what most people do. But a vector is like an arrow is all it is. It's not a geometry ray because a geometry ray goes on forever. Right? As a starting point, it just keeps going and going and going. That's what the arrowhead means usually. But in the vector world, that arrowhead does not mean go on forever. That arrowhead means you stop here. But you came along that direction. So don't think of this as like a ray, like go this way. It's not like that. It's more like a segment. It's got a length to it. Okay? So what I'm saying is if you wanted to draw the vector 6, negative 8, 6, negative 8 looks like this, right? 2, 3, 4, 5, 6, right? Down 2, 3, 4, 5, 6, 7, 8. This vector is pointing the same way. It's pointing the same direction as the first one I drew, isn't it? The run is 3 and 4 on the first vector. The run and rise is 3 and negative 4 on the first vector. The run and rise on this vector here is 6 and negative 8. It's the same ratio. In other words, it's pointing the exact same direction. But what's the difference between this last vector and this first one I drew? The length is different, right? Now the length is not 5. What's the length now? 10, that's right. So this is not the same vector either. These 3 vectors are all different. The first 2 have different orientation or different directions. The first and last ones have different lengths, but the same direction. So it's important that we understand a vector is something that has a specific direction and a specific length. It's a certain way, but it's like a segment because it has length. All right. So how do we get the 5 anyway? Pythagorean theorem. Yeah, that's easy. Pythag rule, right? Just do 3 squared plus 4 squared equals what squared? Okay, so that's not going to be hard. What is HMT method? So HMT method is where sometimes they'll tell you, let the tail be at P negative 1, 3, and the head be at Q 4, negative 5. Write the component form of the vector. So write the component form of the vector. The vector's name, I guess, would be PQ, or you could just, you don't need a name for it, really. Okay, that's actually the symbol for ray PQ. If you want vector PQ, you're supposed to just kind of do a half arrow like this. Like that. Okay, so what does the vector PQ look like? Well, you would want to find the actual run and rise, you see. So how would you find the run and rise? You need to maybe draw a picture. Okay? So you could draw this real quickly. Left 1, up 2, 3. This is the tail of the vector. And then right 2, 3, 4, down 2, 3, 4, 5. This is the head of the vector. So the vector actually points from tail to head, of course, like this. And you could actually just count the spaces. How many spaces is the run? How many spaces is the rise? 1, 2, 3, 4, 5 spaces this way. And then down 2, 3, 4, 5, 6, 7, 8. So this is the vector 5, negative 8. But there's a faster way and a better way, more reliable way to get that answer. Can someone tell me what it would be? Yeah, it'd be smarter to just do subtraction here. So to get that, yeah, to get the run, the 5, you could have gotten that by comparing the negative 1 and the 4, right? Specifically 4 minus negative 1. And you could have gotten the other value, the negative 8, by simply doing negative 5 minus 3. But you definitely want to do head minus tail, because if you do tail minus head, then you will get the wrong direction. So that's what HMT method means. It means head minus tail method. Head minus tail. So let's title that. HMT means head minus tail. Now you might think, I do not need that to figure out the vector. I can do that in my head. That's true. But know that when you're in 3D, the HMT method will give you the vector every time correctly. But if you're in 2D, you might not need a method. You can just count spaces. It's just hard to count spaces in 3D pictures. So HMT will get you the vector in 3D. Okay, standard representation is when you put it right at the origin. So you could actually take, this is cool, you could take this vector, let's call it U. So this is vector U. I just titled it right here, in case you can't see. I just titled this vector U here, okay? And you could actually move it to the origin. So now that you've determined the components, you could actually put it right at the origin. Like that. And you have not changed the name of the vector. So vectors are fully translationally symmetric. That means you can put them anywhere you want in the universe, and it will not change the name of the vector. The only thing that changes the name of the vector is when you reposition it so that it's like tilted at a different angle, or you stretch it or shrink it. So if you make it shorter or longer, you have to change its name. or if you rotate it, you have to change its name. But you're allowed to put it anywhere you want in space. You can even put it on Windows if you want. Okay?
Like this.
Yes. But it would be the same vector. Okay? You would not change its name. So moving a vector around on the paper, just keep it as vector u. If you re-aim it a different direction, change its name. Change it to vector v or something. Okay, so let's study this vector a little bit more. 5, -8. This vector is basically going to be a certain length, right? So to get the length of that vector, you can just use Pythagorean theorem. You have a triangle, basically. It's a right triangle with sides 5 and 8. So you could easily find the length. We call it the magnitude, but it really just means length. We'll find the magnitude by doing square root of 25 plus 64. Square root of 89. Okay? And you can do a decimal on that if you want. It's 9.434. You could also find the direction, because those are the kind of the two most important things about a vector. To find the direction, you might want to use an inverse tangent sort of thing. So if you kind of look at this right triangle, you know the legs, so you could use a tangent is opposite over adjacent idea to get the angle. The angle is usually measured from the positive x-axis. So that's good because that's the same way we measured angles when we did unit circles. Remember, back in pre-calc trig stuff, we always measured from the x-axis. So fortunately, vectors were designed the same way. That's good. So we can measure that angle by doing tan theta is 8/5, -8/5, technically. So this is -8/5, and you will need your calculator for that. Make sure you're in degrees mode, if you like degrees. I suggest you use degrees. If this is in radian mode, it looks a little different. It looks like -1.012 radians. But most people, when they look at -1.012 radians, they don't really know what that means, right? I mean, how many radians is that? I mean, how many degrees is that? So I did inverse tan. I shouldn't have done equals there. I should have done arrow. I did inverse tan of -8/5. Yeah, inverse tan of -8/5. Let me do an arrow there. So theta came out to this. And you can write it in either form. I don't care, just as long as you know which form it is. And title it degrees or radians. Okay? All right. Polar component form. Polar component form allows us to rewrite this vector 5, -8 like this. Put the magnitude on the outside, and then on the inside, write cosine -57.995, comma sine -57.995. This is actually the same exact thing as 5, -8. It's exactly the same. Okay? The difference is just what it looks like, right? So when you look at this, you think, oh, right 5, down 8. When you look at this, you think, oh, let's go 9.4 spaces in this direction. But it's the exact same thing. Both of them mean the same vector. This block can be thought of as right 5, down 8, or it can be thought of as, let's go 9.4 at a diagonal direction. Which diagonal direction? -58 degrees. So this is kind of a polar version of that. That's why it's called polar component form. And for some reason, we leave the 9.434 outside, although you're welcome to distribute it if you like. Also, if you hate negative angles, just go ahead and add 360 to it. There's no consequence to that at all. Right? You can always just add 360 to your -57.995. You could write it as 302 is what I'm saying. .005. Nothing wrong with that if you don't like negative angles. Make sense? Okay, so feel free to use positive angles if you wish. So what are my takeaways from this page? The formulas that you have to know? Well, you have to know kind of how to draw a vector. You have to know that the magnitude of a vector
a comma b is square root of a squared plus b squared. Okay? And you need to know that the direction of a vector AB is inverse tan B over A. Now this second formula you got to be real careful with. Let me show you an example where this second formula does fail sometimes. Let me show you how the second formula sometimes does fail us. Okay? So let's say that you're given this vector, find the magnitude and direction of -3, 4. Okay, -3, 4. That is one of my favorite vectors. Do you have a favorite vector?
Yeah.
Juna has a favorite vector. 1, 2?
Yeah,
Okay. Are you a drummer? Are you a drummer? No.
Oh, no.
That's a beat, drumming beat, a 1, 2 beat. Never mind. Okay. So, -3, 4. I like that vector. What's the magnitude? That's pretty easy. By the way, we usually write the magnitude, if this is vector u, we do absolute values to show that we're finding the length. But anyway, 9 plus 16 square rooted, what's that come out to? 5. So pretty easy calculation there. One of my reasons why it's my favorite vector. 5 it is. Okay, what about the direction? Well, if you get out your calculator and you type in theta equals inverse tan of 4 over -3, the calculator is going to lie to you and tell you that the answer is -53.130 degrees. I don't believe that for a minute. Why don't I believe that? I don't trust the calculator at all. Now, if I add 360 to that, it gives me 306. I still don't trust it. Do you know why I don't trust it? Yeah, Kevin?
Because the vector -3, 4 should be quadrant 2, and then because it gives us the angle of -53 is in quadrant 4.
Yeah. So what's going on is the calculator is lying to you, and it's telling you that you're dealing with this vector, 5 units long, pointing in the direction -53 degrees. That can't be right. The vector was -3, 4. -3, 4, doesn't that mean left 3, up 4? Shouldn't that look more like this? This is the vector -3, 4 in a standard representation, not that black thing. What's that black thing? Why is the calculator lying to me? It's just straight up lying to me. Shame on it. Why is this happening? Okay, so the reason is there are many, many, many angles whose inverse tan is negative, or whose tan is -4/3. Okay, there's an infinite number of angles that the calculator could have given me, you see. And it's not the calculator's fault. The programmers of the calculator told it to give answers only from quadrants 1 and 4. If I remember that from pre-calc days, when we answer inverse tan questions, we've always picked from quadrant 1 and quadrant 4, -π/2 to +π/2. So the calculator's just doing its job, and it's giving us the wrong answer, see? So here's a little caveat to this rule. If you are in either quadrant 2 or 3, you have to add 180 to whatever the calculator says. So we're going to update this formula so you never get it wrong. Instead of theta is arctan B over A, we're going to qualify that by saying it is arctan B over A plus 180 if A is negative. This captures the quadrant 2 and quadrant 3 cases where the horizontal component is left first and then up or down. If you add on this little bit to this formula, you have 2 great takeaways for this part of the lesson. You could pretty much ignore most of what I said and just memorize the 2 formulas there. Okay? But be careful to memorize the full second formula, or you will regret it. Okay, that is a conditional add 180 there. All right, everybody got those 2 formulas? Okay, let's talk about what do you do with 2 vectors in the same problem. Okay, so adding vectors. So if I told you you needed to add, let's say, the vector 500, 0, and the vector 70 cos 60, 70 sine 60, you probably would just get your calculator out and add the x's and add the y's. That's probably what you'd do. You might first want to figure out what 70 cos 60 is and 70 sine 60, right? So it turns out that, yeah, 70 cos 60 is just 35 is all that is. Because cosine 60 is a half. And 70 sine 60 is really just 35 root 3 is all it is. Because it's 70 times root 3 over 2. So those are more compatible. See, we have the component form. These are called rectangular component form. Both of them are ready to add. So you can just add it together without a calculator is what I'm saying. So you don't really need a calculator to do the addition part. But your answer is going to be in rectangular form. So that just means 535, comma, 35 root 3. So I think everybody would have added those properly, especially if I'd given it to you like this in red. You would have just assumed, I think I'm supposed to add the x's and add the y's, right? So let's talk about why that's the case. Whoever invented vectors actually decided that adding vectors would consist of two phases, adding the x's and adding the y's. So why is that? So let's talk about the vector 500, comma 0. What does that mean? So 500, 0 is a very long vector with lots of run and no rise. 500 units of run, no rise at all. Okay? The other vector was 35 and 35 root 3, which is, of course, a much shorter vector. In fact, its length was 70. See this right here? This was the magnitude right there. This was the direction. So it's a 70-unit vector pointing in the 60-degree direction. Okay? And we're trying to add these together. So the people who invented vectors wanted for us, when we add vectors, to treat it as an additional portion of a journey, sort of. So, for example, if you've already traveled 500 miles to the east, we're now going to travel 70 miles northeast from where we left off. So this is the vector 70 cos 60 sine 60. You see? Or you could write 35, comma 35 root 3, your choice. But what is the overall answer? 535, comma 35 root 3. If you graph that vector, it looks just like this. It is as wide as the width of both vectors and as tall as the height of both vectors. So this purple one is a third vector, which is the sum of the two journeys, the red and blue. Hey, that worked out good for me. Red and blue does make purple. I did not intend for that, but if you add the red and the blue, you get the purple one. What is its run? Well, its run is the first 500 miles, you could say, and then the other 35 miles. See? So the total length of that is 535. And then you go upwards. How much? 35 root 3. That's what we did when we did the red. We went up by 35 root 3. Okay, because this is its own vector, this purple thing, it too has its own length, of course. But you can't find its length by adding 535 and 35 root 3, or adding, 500 and 35 root 3. You're not going to add those. You're going to just find the magnitude. So you're going to actually recalculate the magnitude. This thing is called the resultant vector, and we need to measure it. So that's my next little topic here. This is called the resultant. And to measure it, you just find its magnitude. Square root of 535 squared plus 35 root 3 squared. Let's do that real quick. So 535 squared plus 35 root 3 squared. Don't forget to square root, right? About 538.424 miles or whatever. So if you travel 500 miles north, or 500 miles due east, and then you go 70 miles north
geometric meaning should be this, that the final resulting answer is a summary of the journey taken by the cards. So blue and red adds up to purple. The purple is a shortcut for the blue and red travels. And the cool thing about vectors is if you add, let's say you have 15 different vectors, and they're all pointing different ways, if you stack them head to tail, head to tail, head to tail, you create this pathway, and the sum of all those vectors is the shortcut between starting point at the first vector and ending point at the last vector.
So I'll draw that real quick for you. It's pretty cool. Let's say you want to add vector u and vector v, and you got a really long vertical vector w, and you got a vector here, maybe vector x. Okay? The vector u plus v plus w plus x is this one. Both mathematically and geometrically. Like when you actually add the components together, it's exactly what you get every time. And that green one, of course, has its own magnitude and its own direction. Let's go back to our first example there with the purple. What is the length 538? What is the direction? For that, you would just use inverse tan of 35 root 3 over 535. So I would not expect much angle here. Let's try it real quick. 35 root 3 over 535. And don't forget the inverse tan. And I'm in degrees mode. This is only 6.465 degrees. In other words, if you travel really, really far to the east and then just a little bit north, that angle's not going to be very big, right? I didn't expect a real big answer. Okay, what is an opposite vector? That's pretty simple. Opposite means wrong way, right? It means the other way in math. Most of the time, that's what it means. So if I said, hey, graph, or let's find the standard representation, that means graph at the origin. Draw the standard representation vector. Or standard representation of the vector, probably sounds better. Opposite 3, 5. What does that mean? Well, opposite usually means wrong direction in math, right? Or other way. So you would just draw it backwards. In other words, you would draw the vector -3, -5. Okay? So this is the vector 3, 5. As in a standard representation. -3, -5 would be this one. It's exactly opposed to it. Equal and opposite, you could say. Don't take this for granted that we just distributed this negative, okay? The inventor of vectors had to allow that. So whoever invented these symbols had to state things like, it's okay to distribute a negative. And then they explain why it's okay. It's okay because this means right 3 up 5, this means left 3 down 5, and this means the opposite of right 3 down 5. I mean, right 3 up 5. So this would also mean left 3 down 5. So they're just, everything was invented very carefully, so you could kind of distribute that negative and not worry about it, which means you can subtract vectors. So if someone ever asks you, hey, subtract these vectors, 4, 6 minus -2, 5, you should feel every freedom to turn this into an addition problem. Just negate your second vector. Right? Just find the opposite. In other words, distribute that negative. Then just add it up. So what's my resultant, or my answer? 6, 1. Right. Okay, so real simple stuff there. There's your answer, 6, 1. Okay, scaling vectors. So you can also make a vector longer or shorter. Let me show you how to do that. You might finally understand what the word scalar means from this lesson today, if you've never really understood that word, or why it's called that. Okay, so let's say I asked you to find 2 times 4, 6. Do we have permission to distribute the 2? Turns out we do. This is the same as the vector 8, 12, and here's why. 4, 6 looks like this. Right? This is 4, 6. But 2 times 4, 6 can also be interpreted as 4, 6 plus itself. Right? 4, 6 plus 4, 6. The same thing as 2 times 4, 6. So that means you could treat this as vector addition. So your first leg of the journey is right 4 up 6. Your next leg of the journey is right 4 up 6. So this takes us to all the way out to the point 8, 12. So you go, basically what I'm saying is you can go right 2, 3, 4, up 2, 3, 4, 5, 6. Right 2, 3, 4, up 2, 3, 4, 5, 6. In other words, you just get an exact duplicate of that vector. Right here, here's another 4, 6 vector. You see? A little too far there in the x direction. We'll fix that. So we went right 4, up 6, right 4, up 6. But if you look at the resulting travel, the shortcut, or as the crow flies on this, it is just the vector 8, 6. 8, 12. I'm trying to give you permission to distribute that 2. Okay? So this number out front, when you're working with vectors, a number like 2 like that is often called a scalar. You've probably heard that word before. Can you see now why it's called a scalar? It literally scales the vector. It literally makes it longer. A number like this has one job in life in the vector world. All you can do is lengthen or strengthen a vector. This is my own word, strengthen. You like it? Strengthening. Okay? Lengthening and strengthening. That's what numbers do. Now this one lengthens. What kinds of numbers would strengthen the vector? Fraction, right. For example, 1/2 would shrink the vector, right? Okay, so let's play around with that idea for a minute. It sounds like we can actually shrink vectors too. How would you find, let's see here. What would this mean? One half of 4, 6. What do you suppose that means? Do you think it means 2, 3? Yes. It does. So by our previous argument, we would say, okay, I need 2 vectors which are the same that add up to 4, 6. That would be 2, 3 and itself 2, 3. So you can distribute this. Okay? I think it would be interesting. You might think it's random, but I think it would be very interesting to divide not by 2, watch this, but by root 52. Why would Mr. Short want to talk about this special case? What's so important about root 52?
It's going to be a vector. No.
Mr. Short is shrinking this vector by a factor of root 52. Why did he pick root 52? Not root 66, root 52. True?
Yeah, but it's the
Why does it
it's the magnitude.
What?
It's the magnitude. That's what I was trying to say earlier, but I didn't say
It didn't come out.
it.
Okay. I chose root 52 because that was the magnitude of 4, 6. So what happens when you scale a vector down by its own magnitude? That's called a unit vector.
Okay, I was right.
You're right. It's the unit vector. So this guy is a special case of shrinking. You could say, this is the special case of shrinking. Right here. I just took 4, 6, and what I did was I shrunk it down by its own magnitude. Okay? So I am 60 inches tall. No, I'm 70 inches tall. 5'10". I'm 70 inches tall. What would happen if I went and divided every dimension of my body by 70. How tall would I be?
1 inch.
1 inch, correct. I would be a unit shore.
A unit vector.
A unit vector. Yes.
Yes.
Okay. How tall are you, Kevin?
Tall enough.
Wait, in feet?
Just, yeah,
No, in
feet.
centimeters.
Yeah.
I'm like 5'11".
In any other country, he would answer in centimeters.
Yeah, no, that's true.
What?
5'11".
You're 5'11", so you're 71 inches tall. If we divided you by 71, we would have a unit, Kevin. That's what a unit vector is. A unit vector is just a diminished version of a vector, specifically one with length 1. So the only way to make Kevin a height of 1 is to divide him by what? His own height. Yes, his own magnitude. That's the only way you're going to get him to be height 1. Okay, so unit vector, for example, if I say find the unit vector for 3, 4, if I say find the unit vector for 3, 4, well, what's the magnitude of a 3, 4 vector?
5.
Clearly 5. So the answer would simply be 3/5, 4/5. That's not hard. Okay? Which means that there is a relationship that you see in your physics book quite often you may be mystified by. It looks something like this. You'll see this a lot in textbooks. U is magnitude U times U hat. What in the world? What does that mean? Well, if this is the vector U, this is its unit vector called U hat. Okay? U hat. Yes, it's pronounced hat. Which is interesting because the Vietnamese symbol here is pronounced hat.
Nowadays.
Yeah. So it'd be easy for you to remember. But this statement is not very hard to understand. What
It's
is
still the
saying-
same vector.
Listen, this is just saying a vector is made up of its magnitude times its unit vector. Or you could divide by this, and it would be a vector divided by its own magnitude is the unit vector. So you could write it like this if you want. A vector divided by its unit vector, a vector divided by its own magnitude is its unit vector. So you'll see this all the time in your physics class. You'll see these little hats and things. And it's just like saying a shore is like 70 unit shores. That's what it means. That makes perfect sense if you think about it. Where's the 70? Well, that's my height. Yeah. So what are my takeaway formulas from this page? Not very many. Just that you can add vectors. You can analyze the resultant vector. And maybe just to find a magnitude or find a unit vector, you just take a vector and you just divide it by its own magnitude. This might be a good takeaway. So that says square root of a squared plus b squared on the bottom there. On both of them. Okay? By the way, if you go back and you look at this 3/5, 4/5 that I did earlier, and you find the magnitude, what would you expect to get?
3, 4. Or just came 5.
What's 9 plus 6, what's 9 25ths plus 16 25ths? 1. Of course you would get 1. It's a unit vector. It was designed to have a length of 1. But it's neat to see that work out. Okay, so what do the calculus problems look like? What do the calculus problems look like? That was a lot of intro to this. Some of you already knew all that. Okay, some of you didn't know any of it. Just follow the takeaways. If that was new for you, if that was all new for you, just get the takeaways, okay? All right, so our example says find a unit vector that is tangent to y cubed minus, or y cubed equals x cubed over 2 plus 4 at x equals 2. Okay? Good luck drawing this. Good luck getting your graphing calculator to draw it. It's a pretty goofy looking curve, okay? You could probably isolate y here, but we shouldn't need to understand the question. First of all, tangent implies that we need to find the derivative, right? If you're going to be studying tangent lines or tangent vectors, you're going to need the derivative. So let's go ahead and find the derivative here. It's 3y squared y prime equals 3 halves x squared. That's our derivative. Isolating, so we have our derivative explicitly defined. These 3's cancel out. So we just have x squared over 2y squared. Okay, so it sounds like if we're going to get our derivative, we're going to need to have both x and y. So going back to here, we saw that we were given x equals 2. We also need y for our derivative, don't we? Okay, any suggestions? How are we going to get the y, Chloe, for our derivative? Plug it into which formula? We've got 2 on the board. We've got a derivative right here. And we've got the original function. Which one will help us find y? The green one, right. So the green one's job is to plot, right? The blue one's job is to give us slopes. Okay. So let's go ahead and plug in the 2. That way we'll have a y value to go with our x value. But this just comes out to be 8. In other words, y is also 2. So now we're ready to find y prime. Y prime at the point 2, 2 is x squared over 2y squared at the point 2, 2. In other words, it's 2 squared over 2 times 2 squared, 1/2. Okay, are we done with this problem? No, we seek a vector. Listen, we seek a vector whose rise is 1 and whose run is 2. Well, that's not hard to create. How about the vector 1, 2? Or no, 2, 1 actually. I can actually think of another answer though. 4, 2. Yes. Or how about this? -2, -1. Right? Okay, the problem with these is these are great vectors. And trust me, they are perfectly tangent to the curve at 2, 2. So what's going on is we have this goofball curve. Okay? It's actually not that hard to understand. There's this kooky looking curve, and if you go out here to 2, 2, the slope is 1/2. We just created a unit vector. We just created a vector that aims in that direction. Okay? The green one is the 2, 1. The blue one is the -2, -1. See? Like that. The problem is they're too long. These are too long. How long is a vector 2, 1? Rad 5. Good. The length of this thing is √5. Too long. I said I wanted a unit vector. How long is that? Length 1. So what do I need to divide this by? Its own magnitude, rad 5. Correct. So if I now throw in over rad 5 here, over rad 5 here, over rad 5 here, over rad 5 here, what effectively happens in our graph is that those guys shrink. They scale back. So let's fix them now. The green one will scale to be length 1, and so will the red one. So the green one is now length 1, exactly. And I meant to say the blue one. The 2 will turn out to be length 1. Perfect. That's exactly what we wanted. This should have a rad 5 and rad 5 everywhere. And you guys are welcome to leave the radical denominator, but I've seen this question on the AP test. They'll say, find the unit vector that is tangent to the curve at x equals 2. This is exactly what you want to do. We actually just found the slope, and we did rise comma run. I'm sorry, run comma rise for our vector, and we just divided by its own magnitude. What if you wanted vectors that were normal, so unit vectors that were normal to the curve? So the curve is in red here. What if you wanted normalcy, like this way or this way? Opposite reciprocals, right? So how would you modify? These are tangent vectors. Well, you have to flip them over, right? So you want not a slope 1/2, but rather you want the slope to be -2/1, right? Opposite reciprocal. So now this is your rise, and this is your run. So you're going to have to switch these. You're going to have to put the 1/rad5 here, and this is going to have to be like a -2/√5, or what? -1/√5, 2/√5. This way your rise to run ratio is -2:1. The y is double the x, see? And there's units because they have that rad5 on the bottom. These are normal vectors. You should study this example, okay? These are normal to the curve. So that's if the instructions say find unit vectors that are normal to the curve. At 2, 2. And that's the end of the lesson. So this is really kind of the only skill you need to find unit vectors. You also need to know that you can add vectors. You need to know some of the notation. So super long lesson with a full calculus ending, that's all you need. Or lesson, I think that's lesson 1. Yeah. Tomorrow I'll show you how to do velocity vectors and all that good stuff.
Velocity.